And now the next on the agenda is James Bradley from Diffuse Energy in Australia. Good evening, James. I expect you are on right now, is that right?
Yes, Morten, you can hear me okay?
Yeah, okay, good evening.
How are you?
I think it's about 8 or 9 o'clock in the evening in your place, is that right?
Yeah, so yeah, 8 o'clock here now, and I think it was 3 o'clock in the morning this morning when I went to bed after watching some great talks last night. So forgive me if I'm a little bit weary.
No problem. James, you also make a presentation about challenges with micro wind turbine control. Please go on.
No worries. So I'll just quickly share my screen. So firstly, though, thank you very much, Morten, for having us, and I'll briefly mention Fritz as well, who put me in touch with you all the way from the other side of the globe. So it's a real pleasure to be here this evening and talk to everybody. Okay, so hopefully you can all see my screen okay?
Yes.
Okay, so yes, Diffuse Energy is, I guess, a fairly new business out of Australia, making, I think we now hold the record for the smallest turbine to be presented at this this conference. So we put the small in small wind. So just briefly, I'll just give you a quick introduction to us and where we've come from. Some good news about some grants that we've received from the Australian government who are doing some good work in the space, where we see application of our turbines, and then we'll finish up with a little bit about control of micro turbines, which I think is certainly the previous presenter has alluded to the fact that that's probably been a problem for quite some time. So we've done a lot of work in that space. So this is a picture of our turbine, the Highland 920. So it's only 920 millimeters in diameter. It came out of some research from the University of Newcastle, who has a strong wind research group. It's been around for about 30 years. And so my colleague, Joss Kesby, centered his PhD around optimizing a diffuser augmented wind turbine, which obviously gets fairly complicated with the interaction between both the rotor head and the diffuser. So that just gives you some brief specs on what we're all about. And we've concentrated mainly on DC systems and 24 and 48 volt DC. So we don't actually have a 12 volt system. So we've kind of focused on commercial types of systems. So just a bit of where do we come from? So obviously came from the University of Newcastle. We did a program through the CSIRO, which is Australia's science organisation, centred around the commercialisation of university and their own research. They came to the realisation that Australia's done some great research over time, but hasn't done the best job of putting it in the world. And then from then on, we've kind of ticked along, and we're now a full business outside of the university, and have been operating for about 12 months. There was some talk, with some great talks last night by John Niels and Mike Berge, and there were some comments about the lack of funding globally for advancing small wind. We've just been awarded a grant from ARENA, which is Australia's renewable energy agency, to put some micro turbines out in the world in telecommunications towers to better understand how they improve those systems. So out of that, we should get a whole pile of great data and be able to share that fairly globally. So this is a photo here of our test microgrid. So interesting, the language here. So, microgrid's anything smaller than the grid. I thought I'd like to coin the phrase picogrid. I noticed that Fritz has been using picogrid for a long time, so I don't get to own it. But we're talking grids with supplying a load of sort of, 500 watts continuous. So these sites are often remote monitoring sites, remote pumping, telecommunications, so backhaul telecommunication sites. Obviously, Australia is a fairly sparsely populated country, so there's lots of these, and typically they've been running on diesel. And then in recent times, they supplement the diesel with some solar. But to get full autonomy with just solar and batteries, and obviously everyone here knows this, but you need to start oversizing the solar and certainly oversizing the batteries to do so. And so the addition of a complementary input to the solar allows you to make some fairly big improvements, and we'll talk about some of those. So this is some of the use cases that we're looking at. Up in the top left-hand corner is a solar trailer for a tiny home. There's kind of a bit of a thing going on in Australia with tiny homes. The problem is getting power to them. So the getting power to a tiny home here in Australia can cost as much as the tiny home. And so a little remote trailer, and obviously we'd mount a turbine higher than that. That was just so people could look at it. Bottom left hand's on a mine site for their LTE network for radio telecommunications. The center one is a smart street sign. Street signs globally are getting pretty clever and lots of technology packed into them, and obviously to do that you need a lot more power. And it turns out that wind turbines produce more power for a wind loading than a solar panel does. So the problem with putting a panel up the top of a pole like that is the wind loading gets pretty significant. And then in the bottom right-hand corner there is a power system for powering a remote telecommunications tower. So I talked a little bit about batteries before, and this is an interesting use case. So this is a site that we put on a telecommunications site. It's on the top of a mountain in the middle of nowhere. So it's a 48 volt system, a 700 watt load, 2.7 kilowatts of solar, and we go and add a little 200 watt wind turbine and increase the battery cycle time by 25%. So we've basically reduced the diesel loading by 25% and also pushed out battery cycling by 25%, so the batteries will last much, much longer. So it doesn't take much extra input from a secondary input that's not the same as the other to get some pretty good advances. So this moves me to the controller. So we kind of, back in time, patted ourselves on the back for designing a rather efficient turbine. So, a turbine's mechanical efficiency is up around 45%. And thought naively that we would just go out and buy a controller that would control it. And we couldn't. So I've purchased lots of controllers for micro turbines, and none of them really did a very good job. And certainly controllers that will operate at 48 volts are pretty scarce in this kind of size. So we had to go and undertake making our own. And I guess in my mind, small wind turbine, micro turbines, most of their problems over time have been just created by poor control. So, as turbines overspeed or underspeed, they get noisier. And I'll show you some results in a moment. It doesn't take much of an error to have a pretty big impact on the net yield. And so they don't end up performing very well. And all of a sudden the turbine gets the blame. But in my mind, many of the problems have been centered around insufficient controllers. And with upgraded technology, you can do much better now. So this is just a really simplified version of what a boost controller looks like, and I'm probably preaching to the converted here for a lot of you. But in micro turbines, every loss from a voltage perspective gets pretty important because we're typically operating at lowish voltages. And so, we have a boost circuit operating at 50 kilohertz, which is super fast for a boost circuit. The rectifier is an active rectifier, so don't have, we've got very minimal voltage losses through the rectifier. And of course, the boost circuit also bypasses the output diode, so there's no losses there. And we've very carefully selected very low impedance componentry in between, so that our net voltage loss through the entire system is a very small fraction of a volt. And that's been quite a bit of work. And I guess the other thing is that small turbines move really quickly, and so the control system that controls all of this is, operating at 5 kilohertz. So, and we have a totally continuous power curve programmed into it, so it's not a piecewise curve. And so that controller has to work really, really fast. And if you tried to do that, 5 or 10 years ago, you probably couldn't buy the microprocessor to do it. Well, certainly you could, but it would just be too expensive. So I talked about small wind turbines moving really quickly. I just put this in here out of interest. So this is our turbine in a simulated gust front of about 90 kilometers an hour. And that's been let go from standstill to full speed. And you can see here, those two white lines are 450 milliseconds apart, so just under half a second. And the RPM, because I know the conversion, goes from about 600 RPM to 1800 RPM in that time. So untethered, the rotor head can accelerate from 600 to 1800 RPM in half a second. So in gusty conditions, there's an awful lot to control, obviously, in those small time periods. So some evidence of that, this is some data I pulled just out from the other day. So this is from our test site. We logged that test site at 4 hertz. And I know the guy, I think Niels mentioned yesterday that, and I think John did as well, is that appropriate data logging is super important and allows you to make really good improvements, and we've certainly found that. So this site has everything internally to the controller logged at 4 hertz continuously. But you can see here, the bottom plot there is wind speed, and it's changing quite rapidly. It's a reasonably gusty site, but the turbine, if you look at the dark pink trace, is the turbine directly above the anemometer. It's tracking those wind shifts pretty well. So the ability to do that obviously gives you much higher yield than if you missed out on all those little peaks. The other problem with micro turbine controllers is the ability to actually just stop the turbine when things get a little bit hectic. So this is from a couple of weeks ago. This is the record wind speed we've had at the wind farm, which was 108 kilometers an hour. Sorry, at our test site. And you can see a little circled area there. At about 80 kilometers an hour, the controller just turns the turbine off and it rides through the storm, and it turned on about 25 minutes later and kept operating. So, from talking to people, lots of small wind turbines in the past would have just melted something or thrown themselves apart. And this curve, we did this just recently. So the green data there is our original power curve, or the yellow dots is the original power curve that we had in our controller. And after gathering, months of data at 4 hertz and checking out what's going on, realized that there were some improvements to be made once you took, it was based on the mechanical efficiency of the turbine. Obviously there's some electrical things going on and system things and all sorts of stuff to make that not as good. So we modified the power curve and put that back out in the field last week. And that's the blue data that you can see. Now, if you looked at the green data in isolation, you'd say, oh yeah, the controller's doing a pretty reasonable job. Typically, the sparsity of the data is caused during acceleration and deceleration events. So it's kind of to be expected. But between those two curves, which are not that dissimilar, is a 37% increase in net yield of power. And so I guess, had we gone and purchased an off-the-shelf controller that someone else had built, I don't know that we would have had the control to be able to make those modifications. And so I think, you know, doing it ourselves has proven to be pretty valuable. And that's me. So I think I've done 20 minutes fairly comfortably as well, Martin. So thank you very much. And if there's any questions, I'm happy to take them.
Yes, thank you.
I'll stop the
Are
share.
there any questions right now for James Bradley? Anyhow, I think then I might have a single question for you. The last curve you showed us. Yeah.
How much do you have to over dimension your power electronics?
Tony, you have to come here. Yeah.
Yeah.
I'll leave the table.
No, it's okay. It's just a question on how your power curve. You don't seem to have a turbine that's stall regulated. It just continues up. Does that mean you?
After that curve, it is stall regulated. So it's at a higher power than was shown on that chart. That chart went to about, I think, 350 watts. At about 650 watts, we bring on a brake, or slightly less, 550 watts. We bring on a brake which slows down the rotor, and then, like the other chart showed, once it gets up to about 80 kilometers an hour, then we actually just lock the turbine up. So the generator has enough torque that we can short the generator and it just stops the rotor head, or almost stops it. And so at a certain point we do that, and then we just stop the turbine until things are safe again. And those events, you know, are fairly seldom. So you're not losing stacks of power by doing that.
Yeah, because we see the same challenge with a lot of sailboat turbine that just stops the turbine. And what do you do with the excess heat then that you have to deal with in your windings then?
So when we stop it, it outputs about 14 watts into the generator windings, and it's happening at 80 kilometers an hour in an aluminium enclosure. So 14 watts gets dissipated pretty easily. I've had that in a test situation in a wind tunnel for hours on end, just stopping and starting every 6 seconds. With the only thing that gets warm in that case is the bits in the controller that keep switching every. But you know, normally that wouldn't happen in the real world. That was just a stress test, I guess.
Okay. Yeah. So to see that you're trying to deal with the problem. So yeah, good to hear.
Yeah.
Yeah. We have a question from Sean.
Morning, James. I'm just wondering about how far you've got with duration testing and the longevity of these turbines, given that they're rotating at a fair old speed. Are we looking at a 10-year or 20-year life cycle of the product?
Yeah. So if you look at the bearings that we use, they should be the full normal life of a sealed bearing, which is the maximum life of any bearing manufacturers give you is 10 years. So they should do the 10 years of the bearing, because they're fairly lightly loaded for the bearing that they are. We've got, you know, probably a year or so of field data now. And as we put more out, we'll get more certainty around that. But I guess with any new product, the only way you can learn these things is to stick them out in the world and test them. So we've had our test site up for quite a while now, and we've done all sorts of nasty things to those turbines, just to, you know, left them for days in a storm with no load on them, spinning at crazy speeds, just to make sure that things don't break. But yeah, I guess the only way to work out if it lasts for 10 years is to have one going for 10 years.
Yes.
Good evening, James. Just wanted to ask you whether or not there you would foresee any advantages customizing control curves for specific wind sites. Obviously, you've seen some significant advantages at your test site with the revised curves. You have the ability to essentially put custom curves for each individual site?
So the curves track basically the maximum efficiency of the turbine. And so there's no great advantage to changing that curve for a given site, because we're basically tracking the best spot on the curve anyway. And so I guess in gusty sites, we want it to be, it's more about being able to track those gusts fast enough and having a controller that works fast enough.
Yes, that's largely what I'm trying.
Probably not. It's probably more the thing that we need to do is potentially have a different blade set for different regions. So, which is something that we're thinking about. So, for lower average, our blades are designed for a reasonably high average wind speed because we like to put them in nice windy places. But we're finding, like for example, the guys with the street signs, they're obviously often in places that are not as good. So we're looking at potentially designing a new blade set for a lower average wind speed for them. But yeah, probably leave the curve alone, to be honest, because having thousands of different curves out there could get problematic.
Thank you very much, James.
It's all right.
Well, thank you very much. John,
No worries.
Are there further questions? It seems not so. Well, I just want to inform you that the Folkecenter is also building a tiny house. If people are interested, they can follow the project on folkecenter.net. That's just a service information for all of you. But James, thank you very much for your presentation. And we will have a short break till 11:15 Central European Time, but that's about 17 minutes from now. We'll continue with Luis Arribas. But anyhow, I wish you a good evening and hope that you will stay with us for as much as you can on the sessions. Thank you very much.
Okay.
Thank you.
Thank you so much, Morten. Thank you for having me. It's been a great privilege.
Been a pleasure.
Thank you.
Yeah.
Cheers.
Well, we'll just take a short break and be back at 11:15 Central European Time. About 17 minutes from now. Thank you. Have a good break.